Determining exoplanet habitability utilizing transmission spectroscopy. The United Nations Population Reference Bureau predicts that by 2150, Earth will be considered inhabitable because of overpopulation. Overpopulation places stress on Earth's resources, both renewable and non-renewable. Disease rates will increase and environmental pollution will skyrocket. These effects will soon become irreversible. The purpose of this study is to provide more information and analysis for exoplanet candidates utilizing a unique method of combining the transit method and Doppler spectroscopy. The habitable zone is a theoretical area surrounding a star where any nearby planet can support life or have liquid water on its surface. A stable HC has two factors. First, no large mass body should be close to the HC because it disrupts the formation of Earth-like bodies. Second, the HC range should be consistent. All stars get brighter as they age, and a given HC near that star should move outwards. But if this happens rapidly, this gives a planet a weaker chance to develop life. Ergo, that star must survive for a long period of time. Because of those two requirements, most of the stars being searched are F, G, K, or M stars. These letters classify stars based on stellar classification. F, G, K, and M stars are the cooler stars temperature-wise. The blue band in this diagram represents the location of the habitable zone. Notice, as expected, that for low-mass cool stars, the region is closer to the star, and for higher-mass hotter stars, the region is more distant from the star. In this particular illustration, the Earth appears to be precisely in the middle of the HC from the Sun. The transit method is one of the most popular techniques to locate exoplanets. It's based on the observation of a star's small drop in brightness when the orbit of the star's planet passes in front of the star. The amount of light lost depends on the light of the star and planet, and the duration of the transit depends on the planet's distance from the star and the star's mass. Doppler spectroscopy is another popular method. First off, the Doppler effect is the change in frequency of an electromagnetic wavelength from an observer moving relative to its source. It's used to calculate the speed at which stars and galaxies are approaching blue shift or moving away red shift from a source. Doppler spectroscopy involves the observation of Doppler shifts in the spectrum of a star around which a planet orbits. Periodic variations in the star spectrum will occur, where the wavelength of characteristic spectral lines increase and decrease. This may be indicative of the radial velocity of the star being altered by the presence of a planet orbiting the star, causing Doppler shifts in the star light. Together, transmission spectroscopy gathers information about the chemical composition and the extent of the atmosphere of a transiting exoplanet. As the host star's light passes through the atmosphere of the planet, its light is absorbed by the molecules in the atmosphere, making the exoplanet appear bigger. The shape of the transmission spectrum can indicate which elements are in the atmosphere, such as water especially. Bennick and Seeger, 2012, utilized the transit spectroscopy method to infer the atmospheric compositions and surface cloud top pressures of exoplanet GJ1214b. They found a unique mix of the absorbers in two spectrally inactive gases, such as hydrogen, carbon dioxide, and water, to be possible if the findings quantify the broadband transit depths in at least one absorption feature for each absorber. Additionally, the mean molecular mass can be constrained by measuring either the scattering slope or shapes of the absorption features, enabling one to distinguish between cloudy, hydrogen-rich atmospheres and high mean molecular mass atmospheres. Knudsen, 2011, performed nearly the same thing with the Spitzer Space Telescope on exoplanet GJ436b. This graph displays a comparison between measured transit depths, the red circles, and model transition spectra, where the transit depth is defined as the square of the best fit planet-star radius ratio in each band. They found that the level of significance for the changing radius ratios remains high even after accounting for limitations. Berta, 2011, researched the transmission spectrum of exoplanet GJ1214b and recorded observations of its atmosphere. He achieved nearly photon-limited precision in these observations, finding the transmission spectrum of GJ1214b to be between 1.1 and 1.7 micrometers. The transit depth most likely implies a large mean of molecular weight for GJ1214b's outer atmosphere, and a dense atmosphere rules out bulk compositions that explain its large radius by the presence of a low-density gas layer surrounding the planet. The top panels of this graph are transit light curves for GJ1214b, and the bottom panel is a combined transmission spectrum along the spectra for each visit. Each light curve in the top panel is aligned to its respective wavelength in the panel below. As for the experiment procedure, archived exoplanets will be the target of the study, the most likely candidates being Gliese 581d and HT 85512b, because astronomer Abel Mendez, 2005, ranked these with the highest habitability in 3 different scales. Their characteristics will be observed with the Phelps telescopes, which provide access to telescopes in Hawaii and Australia. Recently, Phelps has teamed up with Lowell Observatory to locate astronomical objects, specifically but not limited to asteroids in the Kuiper Belt. Online astronomy simulators, particularly the circumstellar habitable zone software, provide the same service. Using both telescopes and simulators, characteristics such as orbitals, mass, and luminosity can be determined. Additionally, the transit method will definitely be a large component that will be performed with the simulators. The MEADE LXD75 telescope with DSS-7 spectrograph attachment will be used for transmission spectroscopy. Between the time a host star shines upon its planet to the time the planet leaves the light, the spectrograph will be able to retrieve the spectrum of the atmosphere of that planet and determine its composition. This will be the budget. The Manhasset Science Labs already own the telescope and spectrograph. The online simulators are free to use, and the availability to the Falks and Lowell observatories are accessible through username and password. All data will be quantitative and will undergo a Pearson correlation statistical analysis test with Earth's current information. Should things work out in favor, the exoplanet data should result in a correlation value of R greater than 0.9 with Earth's data, indicating very strong similarities. Consequently, the purpose of this experiment is to provide more information and analysis for exoplanet candidates utilizing mainly transit spectroscopy. Gliese 581Z and HD 85512b will be analyzed through the Falks and Lowell observatories, which will record their planetary characteristics. Additionally, transit spectroscopy will be applied utilizing the MEADE LXD75 telescope with DSS-7 spectrograph attachment. All quantitative data will then undergo a correlation statistical analysis with Earth's current information, and a predicted R value of greater than 0.9 will be established. Thank you.